సబ్స్క్రైబ్ చేయండి. ఫర్ మోర్ అప్డేట్స్ బెల్ ఐకాన్ క్లిక్ చేయండి.
Now we are going to discuss Clausius-Cleverness equation. In Clausius-Cleverness equation, in the stage of liquid converted into vapor. So some stages are here observed. First of all, we have to derive the Clausius-Cleverness equation by using by help of the Carnot efficiency of Carnot engine. Carnot's efficiency. So then efficiency eta equals to W upon Q1. Then eta equals to 1 minus Q2 upon Q1. Eta equals to 1 minus T2 upon T1. These are all equations of efficiency of Carnot engine. So first of all, we observed this diagram. In this diagram, there are four processes are done. There are four processes. One is the reversible isothermal expansion, BC. Reversible isothermal expansion, BC. The liquid is converted into vapor. In this position, the liquid is converted into vapor. Here heat energy is given by Q1. Here heat energy is given by Q1. Next, second one is the CE, that is the reversible adiabatic expansion. Reversible adiabatic expansion, same as in Carnot engine. This is the isothermal expansion. This is the adiabatic expansion. This is the isothermal compression. This is the adiabatic compression. So first of all, BC is the reversible isothermal expansion. In this stage, the liquid is converted into vapor. Second one is the CE, that is the reversible adiabatic expansion. So here the temperature drops T minus dt. First original temperature is the T, then the change is the dt. So the temperature drops T minus dt, while the pressure drops same as the pressure drops P minus dP. Third one is the reversible isothermal compression, that is the FE. That is the FE, reversible isothermal compression. Here the vapor rejects heat Q2, rejects Q2 at temperature T minus d theta and gets converted into liquid. Fourth one is the reversible adiabatic compression. Reversible adiabatic compression is the FB. So these are all four processes are here. First one is the reversible isothermal expansion. Second one is the reversible adiabatic expansion. Third one is the reversible isothermal compression. Fourth one is the reversible adiabatic compression. First one is the reversible isothermal expansion. That is the BC. In this stage, the liquid is converted into vapor. Here the heat energy is given by Q1. Here heat energy is the Q1. Here Q1 is equals to, formula is the ml. Here m is the mass of substance. Here L is the latent heat. Then here Q is the ml. M into L, the product of mass and L is the mass of substance, L is the latent heat. So here the heat energy is absorbed at temperature T. Here the heat energy absorbed at temperature T. So the volume increases. Here the volume increases, that is the volume increases means the volume increases means here m v2 minus v1, v2 minus v1. So here the second one is the reversible adiabatic expansion. Adiabatic expansion, that is the CE. So here the temperature drops T minus dt. First temperature is the T, then the temperature drops, that means decreases, that is the T minus dt, while same as the pressure is drops P minus dP. Our third one is the reversible isothermal compression, that is the FE. That is the FE. In this case, the vapor rejects heat Q2. In this case, the vapor rejects heat Q2 at temperature T minus dt and gets converted into liquid. Our fourth one is the reversible adiabatic compression, that is the FB. So in all stages, the work done in above reversible cycle, so this reversible cycle, first start, continuous, end, start. This is the reversible cycle. In this reversible cycle, the work done in reversible cycle, work done dW equals to pdV. Then dW equals to P is converted into dP. Here dV is the difference of volume, that is the V2 minus V1. Here m, total m. So dW equals to m into V2 minus V1 into dP. That means m is mass of a substance. Here the efficiency of cycle. The efficiency of cycle is eta. Eta equals to work done by Q1. Then eta equals to work done is the dW. dW is already, we know that m into V2 minus V1 into dP upon Q1. Here Q1 is also, we know that is the ml. ml means the product of mass and latent heat. Eta equals to m V2 minus V1 into dP upon ml. Here m are cancelled, remaining eta equals to V2 minus V1 of dP L. This is our one equation, first equation. But already we know that this equation written inside, eta equals to V2 minus V1 into dP upon L. This is the first equation. But we know that eta equals to 1 minus T2 upon T1. So then eta equals to T1 minus T2 upon T1. T1 into 1, T1 minus T2 upon T1 L. T1 is the here LCM. So then eta equals to T1 means first temperature, second temperature is the temperature drops, that is the T minus dt. Here T1 is the T, first temperature is the T. So this equation can be written as eta equals to T minus plus minus into minus plus minus into plus minus dt upon T. Here eta equals to T is the cancel, dt upon T. This is the second equation. From 1 and 2, dt upon T is equals to V2 minus V1 upon L into dp. So this equation can be written as dp upon dt is equals to L upon T into V2 minus V1. Here dp upon dt, here V2 minus V1 upon L is in the another side, L upon V2 minus V1. So this equation can be written as this. So this is the Clausius Clapeyron's equation. Clausius Clapeyron's equation. But we now also derived the Clausius Clapeyron's equation from thermodynamic equation. For thermodynamic equation, then this is the Clausius Clapeyron's equation. So first of all, we have to discuss the when a solid is converted into liquid. So some melting points are remaining. So first one is the application. This is also application. Effect of change of pressure on the melting point. When a solid is converted into liquid, there is a change of volume. Change of volume means this is the volume change. The substances like wax and sulfur, so these are all substances expand on melting, then that is the V2 is greater than V1, then V2 minus V1 is positive because second volume is the highest value. So here V2 is greater than V1, then dp upon dt is positive. dp upon dt is positive. In the Clausius Clapeyron's equation, that is the dp upon dt is equals to L upon T into V2 minus V1. When V2 minus V1 is positive, same as dp upon dc is positive. So this means the melting point of wax or sulfur, these type of substances rises with increases of pressure. So the substances like ice which contracts on a melting, V2 is less than V1. Just like as these substances are ice are like these substances, wax and sulfur type. So in this case V2 minus V1 is negative. So then same as also dp upon dt is negative. This means the melting point of ice like substances decreases with increasing in the pressure. Same here in this stage increase of pressure, melting point is rises. melting point is rises. In this stage, melting point is decreases whenever the power is increasing. In this stage, the power is increasing and also melting point is increasing. In this stage, V2 is less than V1, the melting point is decreases, same as the melting point is decreases, then the pressure is increasing. So another effect, of pressure on boiling point. When a liquid is converted into gas, so the volume V2 is already the volume V2 of the substance in the gaseous state always greater than the volume V1. So V2 is greater than V1. Then this stage V2 minus V1 is positive in Clausius-Cleverness equation. Clausius-Cleverness equation is dP upon dt is equals to L upon T into V2 minus V1. Then this stage V2 is greater than V1, V2 minus V1 is positive, then this is also positive, dP upon dt is positive. This means the boiling point of every liquid increases the pressure. The boiling point of every liquid state increases of the pressure. So next, Clausius-Cleverness equation from thermodynamic relations. First of all, Maxwell's second thermodynamic relation is dou P upon dou T at V is equals to dou S upon dou V at T. So multiplying this equation with T on both sides, so then this equation can be written as T. So this is the T into dou P upon dou T, here T into dou S upon dou V. This is the S is the here entropy, but already we know that TdS equals to dQ. This equation from Maxwell's second equation, TdS equals to dQ. Then T into dou S is equals to dou Q. This equation can be written as this: T dou S equals to dou Q. Then here dou P upon dou T at V is equals to next dou S upon dou V. So in the place of dou S can be written as dou Q upon T. So this equation can be written as, so in the place of dou S we substitute the dou Q upon dou T, same as this. So this is the T dou P upon dou T at V is equals to T into dou S is the T into dou S is the dou Q upon dou V at T. In the place of T into dou S equals to dq. So then this equation can be written as dou P upon dou T at V is equals to T 1 upon T dou Q upon dou V at T. But dou Q is the change in heat, that is the dou Q is can be written as L, that is the latent heat. So then this equation can be written as dou P upon dou T at V is equals to 1 upon T dq means here L, dou V means that is the change in volume is means V2 minus V1 at T. So this equation can be written as dou P upon dou T at V is equals to L upon T into V2 minus V1 at T. This is also Clausius-Cleverness equation from Maxwell's thermodynamic equation. This is also Clausius-Cleverness equation from Maxwell's thermodynamic equation. So original Clausius-Cleverness equation is the dP upon dt is equals to L upon T into V2 minus V1. This is the general Clausius-Cleverness equation. This is the Clausius-Cleverness equation from Maxwell thermodynamic equations.